Welcome back, everyone, to the Algebraic Graph Theory seminar. This week we have Alden and Herman from University of Virginia talking about the results of a search for small association schemes with non-cyclotomic eigenvalues.
Okay, so thank you to Sophia and Sabrina for inviting me to give this talk in your seminar. Okay. I'm going to start with a bit of a confession. I think you should always confess when you didn't actually solve the problem. And as you can see from items 2 through 6 there, what we've actually done is something that's sort of common, I think, in problems that involve association schemes and existence issues, where you find a feasible parameter set or a bunch of them for some association scheme you'd like to exist, but you actually have to eventually show that's actually realized by an association scheme. And so that's what we've done. We found a bunch of feasible parameter sets for these things. This acronym SITAWlMs stands for Standard Integral Table Algebra with Integral Multiplicities. It's just an acronym that covers off feasible parameter sets for one feasibility criteria. And probably the most interesting thing is how we search for these, and actually got some of them where I think people hadn't been successful before, just from a bit of persistence and some background issues which helped us be successful in this. So okay, so starting with the confession, I'm not an algebraic graph theorist. We haven't solved the problem. Why am I here? I'm actually working in representation theory. I think most people in the Canadian mathematical community know me as a representation theorist primarily. I do some computational algebra. Probably my best contribution was this calculation of Wedderburn decompositions that's been implemented in GAP, and it's an official GAP package that you'll receive if you download GAP. It's one of two such programs. The other one is implemented in Magma. So basically what you do is if you take a basis of some integral algebra with non-negative integer structure constants, usually that's what this means. When you multiply two things, you get non-negative coefficients when you express the linear combination in the same basis. And often you want the basis to be such that when you complexify it, you get an algebra with involution. Association schemes, for example, are like that. So are the case where B as a group would be like that. And then, since that means that the algebra is semi-simple, it has a Wedderburn decomposition. And when you go back to the defining field, which is rational, then it breaks up as the direct sum of simple algebras over the rationals. Because the field Q is characteristic 0, those centers of these division algebras, these DIs that are occurring in these simple components, end up being equal to the field of character values. So this direct sum is actually over the Galois conjugacy classes of irreducible characters in the complex algebra, but the fields are rational extensions, or extensions of the rationals that you get from the character values. And so that's been implemented, and probably the first 15 years of my career I worked on problems related to that, or in integral representation theory. And then about 15 years ago, I switched gears and I started working on problems that were of interest in algebraic combinatorics. So, and doing the same thing. So you take this basis and you try to extract information from this algebraic decomposition, and even information about the algebraic decomposition. So of interest to algebraic graph theorists, you've got places where the B is the power basis of the adjacency matrix of a graph. Okay, that spans a polynomial matrix, a ring of matrix polynomials that sort of intimately is related to the spectral graph theory of that graph. The set of adjacency matrices of a finite association scheme is another natural basis for for B, where you get a semi-simple algebra from this. If you want to work in the non-commutative world, then you can go to coherent configurations and get pretty much the same problems. There's also interest in decomposing the algebra that comes from the Terwilliger algebra when you put the association scheme and its dual together and work for the Terwilliger algebra with respect to one vertex of the algebra. So if people are interested in those problems, it's something that I've been thinking about lately. Now, in association schemes, there's this question that so you can find it's sort of prominent in the book of Bannai and Ito about whether or not these commutative association schemes have cyclotomic eigenvalues. Okay. Now, these eigenvalues are actually the character values before. Let's see, can I get back? Yeah, these are the character values here in the commutative case. And the question of whether or not they lie in the cyclotomic extensions of the rationals. The cyclotomic extensions of the rationals would be these are the fields that you get by adjoining complex nth roots of unity to the rationals. And anyway, those extensions are in a lot of cases, in a lot of senses, the nicest extensions. And this is something that's naturally true for group algebras, because the elements, the group basis elements, every eigenvalue is a root of unity. So you have to have this property for those. But for association schemes, it's curious that lots of interesting schemes have this property. So in the book of Bannai and Ito, there's a rationale that these are it's true for commutative schemes. They're both P and Q polynomials, so metric and cometric association schemes have this property. Babai's formula for the eigenvalues of a normal Cayley graph shows that you can express this in terms of the character values of irreducible characters of a group. So this means that those values will lie in a cyclotomic extension. And perhaps not as commonly known is that we do have a paper on this. I have a paper on this with Amir Ranamai Bargi, I know in about 2008. It's one of our first contributions on this. That is true for commutative quasi-thin association schemes. Quasi-thin association schemes are valency 1 or 2. And it's for a little bit more. If you have association schemes where the valencies are 1 or 2, or if you have perhaps one of valency 3, or perhaps one more of valency more than 4, then this is still true, and this is proved in our paper. Now, I should say quasi-thin association schemes are a class that they call Schurian, and so they're almost all of them are Schurian, and they're covered by a later result of Spiga and Musicek. But the ones that have this exceptional valency are not known to be covered by that. And it's curious that if we have one valency 4, that our proof doesn't work. So yeah, that's an interesting question that hopefully gets people interested. Now, when you go to the non-commutative world, if you drop the commutative assumption, work with a homogeneous coherent configuration setting, the answer is no. In the classification done by Hanaki and Miyamoto, you can find 2 non-commutative association schemes of order 26, where the valency, the adjacency matrices that occur in the scheme themselves have non-cyclotomic eigenvalues. The fact that they're Schurian is curious, because that means that they're in double coset algebras of groups, which means they're quite closely related to groups. In last year, my student Regea Maleki and I, this is the work I'm talking about with her, have a different work where we found two non-Schurian association schemes that of order 32 that have this, and a lot we actually searched up to order 200 and found lots and lots of them. These have transitive automorphism groups, and we found them looking at Schur rings. So even in the association scheme world, you have Schurian association schemes, which are double coset algebras, and you also have Schur rings, which are a different class that have transitive automorphism groups. Then you have a third class that have intransitive automorphism groups, or even sometimes trivial automorphism groups. And those you can only approach by fusion. Oh, there we go. Now, for these non-commutative, in the non-commutative setting, you still can ask a question about character values. So the irreducible characters, if I label them chi0 through chi s minus 1, the s here can be less than the rank, the dimension of the scheme, then you can ask if the character values lie in the cyclotomic extension of Q. Now, these character values are actually sums of eigenvalues of the adjacency matrices of the graph. And so they can be sort of normalized. The non-cyclotomic parts can be normalized out. And that's what seems to happen. We, in our search for these Schur rings of order up to 200, we didn't find any that had non-cyclotomic character values. So there still is a question that applies here. And for these, we have some partial answers. So for Schurian association schemes, these are double coset algebras, and their simple components are Morita equivalent to simple components of group algebras. And so the answer is yes for those, because the center is Morita invariant. So it's even for the non-commutative ones. The answer is yes. And yes for all small association schemes, because we can just look in Hanaki's classification, Hanaki and Miyamoto's classification, and check, and this is indeed the case. Now, but I have here in the bottom line here, all closely related situations, the answer is no. So what closely related situations would you want to check? An association scheme is a decomposition of the complete graph into graphs or totally directed digraphs, where the identity is included, the adjacency matrices of the graphs that you make are algebraically cohesive. So that means when you multiply to them together, you get a non-negative linear combination of the actual adjacency matrices of the elements in your decomposition, and also closed under the transpose operation. So you can ask, and part of that, one of the features that they have is that the graphs or digraphs involved are regular. They have to be regular, and so you can look at regular graphs, and for those, if you look at all regular graphs of a certain order, the answer is no quite immediately. Order 9, you already get non-cyclotomic eigenvalues occurring, and by order 16, almost all of the regular graphs have non-cyclotomic eigenvalues. So it's very no for regular graphs. If you look at the algebras that association schemes generate, these are a type of algebras called standard integral table algebras, which I won't bother to define, but you can look at those as well. And if you look at standard integral table algebras of small order, you quite quickly find non-cyclotomic ones with non-cyclotomic character tables. So these already happen at order 13 and dimension 4. So the answer is really no for those as well. Another closely related situation is the case of fusion rings, and in particular, the most interesting fusion rings are categorifiable fusion rings. And there, about 5 years ago, there was a paper by Morrison where they found fusion rings with non-cyclotomic eigenvalues of dimension 5 or 6 or something like that were generated using subfactor theory. And so the answer is again no in that case for interesting fusion rings with pretty small dimension. So there is another result that probably people know more, because there's an Annals of Math paper that proved that the Perron-Frobenius dimension of these things does have to be cyclotomic, these fusion rings, but that's just for the first character. That's just for the valency character. So that's not exactly what we're doing here. The character tables can be non-cyclotomic for those people who may know something about that related area. So what does this evidence tell you to do for this problem? It tells us that if there's a counterexample, if you look for a counterexample, you could find one that's quite small. Now, it won't be immediate because, I mean, this problem's been around for 40 years. But perhaps if you push the envelope on small counterexamples, you may find something, or at least find some better evidence as to why it could be true. So that was our approach to look for things like that. Okay, now let me get into some of the parameter sets for association schemes, and I'm sorry for people that might be in this area. I'll probably bore you a little bit with this, but I'm going to look at these parameter sets from the point of view of what would you look for if you're trying to find a smallest counterexample to this non-cyclotomic eigenvalue question. Okay, so look at it from that perspective. Okay, so the first parameter sets for association schemes come in sort of a collection of 4 things. So the algebra itself defines the first parameter set, which is the intersection numbers. These are just the structure constants themselves for the basis of adjacency matrices. So these non-negative integers in Ij, I hope you can see my cursor moving here so that you can see this. So these are these non-negative integers. They have lots of properties that you can find in books on association schemes, because this is, it's an associative algebra. In some books you assume it's commutative, so it gives you a bit more. I've been talking about valencies. The valency is this structure constants that you get when you multiply AI times AI transpose. Now, AI transpose in the notation is indexed by I star. So I guess I'm doing, if AJ transpose is AJ star, where the star just changes the indices, then the structure constant of the identity, the A0 is the identity as I've got it up here, is what we call the valency. Now the AJ graph or digraph is KJ regular. So it's a natural graph invariant for this element of this association scheme. Okay, and so that's another parameter that you need to know about. The valencies are always going to be non-negative. They're going to be positive integers, okay, in this scenario. Now, because you have if you're a representation theorist and I give you the structure constants, you say, great, I've got the algebra. And so how do you get the algebra? You use the structure constants to get the left regular representation. So this is the operator that you get when you multiply things in the algebra on the left by AI. So you're mapping AI to this R by R matrix VI, R being the dimension of the algebra. And what you do is you just take the structure constant as the expression of that product, AI times AJ, in the basis of adjacency matrices, ordered adjacency matrices. So all you have to do is just read these Nijs for specific K and J as a column. So you would take the kth column of your regular matrix for BI and write down the Nijk elements in order. Okay, so this is just standard linear algebra things, and you then get a collection of R by R matrices which multiply exactly according to the structure constants you started with. This is the trick. Okay, so it gives you the algebra, but now with a much smaller dimensional representation, and actually smallest possible representation. So that's your regular representation. Those matrices are what we call the intersection matrices for the algebra, and they're a type of algebra which I call a standard integral table algebra, and you can find definitions for all this. This terminology is due to R.V. Blau, and you can find this in some survey papers of Blau, what these terms really mean. I'm going to call this algebra, this type of algebra, a SITA, standard integral table algebra. Okay, and so that's from my structure constants, I get those parameters. And I get this algebra automatically that's related to my scheme. Of course, remember, we're in a situation where our scheme may or may not exist. But this algebra, if I know the structure constants, it will exist. Okay, and then from now these intersection matrices, I can then write down their the characters of the algebra, so the irreducible characters of the algebra. If it's commutative, these are just going to be the projection maps to eigenvalues in the algebra. So your algebra being commutative will be completely diagonalizable. So that means you can turn it into a set of diagonal matrices and multiply them according to the rules where you have these common eigenvectors, and projection with the common eigenvector is the character chi I on all of the BJs. Okay? So your character table is this matrix which gives you the character values. In the non-commutative world, then these would be sums of eigenvalues, but here I'm going to just talk about commutative ones today. Okay, so if this R-dimensional algebra is commutative, then you can join all of the eigenvalues or character values, whatever you call them, to the rational field, and that's going to give you, in this case, the splitting field. If you're doing the non-commutative things, the splitting field is a little bit more difficult to describe, but in the commutative world, this is the splitting field, and the number of irreducible characters in the if you're working over commutative schemes, will be the same as the dimension of the algebra. So the S will be R. And so your character table will be an invertible R by R matrix. This is in Bannai and Ito's book called the first eigenmatrix. And the columns of P are just the entries where you list the eigenvalues of each Bj or Aj. They have the same eigenvalues, as it turns out. And so you can, if you're looking at this from the point of view of looking for a non-cyclotomic scheme, you're looking for, are the entries of these columns of P in a non-cyclotomic field? So how do you tell if it's in a non-cyclotomic field? Well, you have to check the Galois group of that field that you get. So the Galois group of the field that you get, and by the Kronecker-Weber theorem, something that comes from class field theory, this Galois group should be non-abelian if and only if you have some non-cyclotomic eigenvalues. So you have a nice way of checking this. In GAP, we can use the Galois type command if we know a generating polynomial for one of the non-cyclotomic roots. So you have a non-cyclotomic entry of the character table, and if you know it's polynomial, then you can check whether or not you have a non-cyclotomic eigenvalue or not. Okay. And that command actually works pretty well up to dimension 12, and it theoretically can work up to dimension 15. So we have a good chance of being able to find something interesting for our small examples, at least. Now, the set of columns of P, if you know those, if you know your character table, then you can actually get back to your structure constants in the commutative case. So in the commutative case, your columns of the character table, they form a basis of an algebra under a component-wise addition and multiplication that ends up being exactly isomorphic to QB. So you can recover your structure constants by just from solving some systems of linear equations, and so that's quite easy to implement as well. This goes back to formulas for the primitive idempotence. This is the reason why this is true. Okay. Now, when your algebra is commutative, you can get the character table of the dual directly from P. So you just take P inverse, you multiply it by n. N is the order, which is the sum of the valencies in your algebra. And you can recover then this character table, what we call the dual character algebra. This is not a it's not a theorem for that's closed for table algebras, but it's closed under character algebra, which can allow some non-negative structure constants, as it turns out. But it's a well-formed theory from the 50s. And so you have this dual algebra in the commutative, again, with one assuming this scheme is commutative. The first row of this second eigenmatrix, this character table of the dual, gives you what are called the multiplicities of your irreducible characters in the same order that you had them before. These multiplicities are always non-negative real numbers, but they don't have to be rational. So when you have Galois conjugate irreducible characters, then they will have Galois conjugate multiplicities. The formulas for them are use row norms of P. So if you conjugate the character, then you conjugate these multiplicities. I should have mentioned that the Galois group of the splitting field always acts on rows because it permutes irreducible representations, and therefore it permutes irreducible characters, and those are the rows of P. So you will have this action on P, which corresponds to an action on columns of the dual. Okay. Now, if I'm in a situation where my standard integral table algebra can be realized as an association scheme, then these multiplicities are actually the multiplicities of the irreducible characters in the standard representation of the association scheme. So they have to be, in that case, that's an actual representation. And so those have to be non-negative integers. And so Galois conjugate characters will have the same multiplicity, and it will be an integer. So that's why if I have a standard integral table algebra that can be realized as an association scheme, it has to be what we call a CETA-WIM, standard integral table algebra with integral multiplicities. This is the first of our feasibility criteria that we need to check in our search. Okay, and probably people already also know about Krein parameters. So if you now play the same game as you did with P to recover your structure constants that you started with, the columns of the second eigenmatrix are a basis for the character algebra that corresponds to the dual when you use component-wise multiplication. And so those you can get structure constants for that algebra, and those are called the Krein parameters. I prefer to do this sort of in a conceptual way rather than formula way, but I'm sure if you look at a lot of books, you find lots of formulas for Krein parameters, but this is how they interact, these parameter sets. Okay, now these Krein parameters are again they're just complex numbers really, and in general for character algebras, the first rows have to be positive, or excuse me, non-negative, but that's not the case for all of them, and they don't have to be rational. So when you join the set of these Krein parameters to the field Q, you'll get a field of Krein parameters, and this is actually the minimal field of realization for the dual. Now, when it's realized by an association scheme, or commutative association scheme, the Krein parameters have to be non-negative. This is a fact that's proved in the book of Bannai and Ito. It comes back to the primitive idempotence being represented as n by n positive semi-definite matrices. Okay, and the Krein parameters themselves are structure constants for an algebra. So it has a left regular representation, which you can also recover with systems of linear equations. And the regular matrices that you get are another family of parameters for the scheme called dual intersection matrices. Again, you do the same as before, where you use these Krein parameters to make a regular representation and build your structure constants. So our regular matrices are the same as having the structure constant for the algebra. That determines your character table. P determines the dual character table. Our second eigenmatrix, which determines your Krein parameters, and that determines your dual intersection matrices. All of these parameter sets are equivalent for CETA-WIMs. Now, the one fact that was known about this paper by Munamasa, which basically says part 2 here, that the Galois group of the splitting field over the extension that you get by adjoining Krein parameters, it has to be central in the Galois group of the splitting field over Q. It's a curious thing. And the way that's proved is that these extensions which fix the field of Krein parameters will be realized as permutations of columns of the character table. And it's not too hard to show that those have to be central in the Galois group. And a byproduct of that means that the Galois group extension of L over Q can't be cyclic. Otherwise, your Galois group itself would be abelian. And so that's a barrier. So that makes these non-cyclotomic association schemes, if they do exist, it makes them quite strange objects that their duals are not even close to being rationally realized. That's what this is telling us. Okay, so now how did we do our search? So we start with the parameter set information, okay, which means we need our multiplicities, our dimension, and that's about it. Oh, sorry, my mouse is acting up on me. We take the regular matrices, we treat their entries as being unknowns, and then apply all of the structure constant identities that would come from the table algebra, standard integral table algebra features to get lots of polynomial identities in the variables that come from these entries. These generate an algebraic variety, okay? This kind of approach was used. I think there's a book that's edited by Misha Klin and Musachuk on this from about 10 years ago. I don't think it's a very novel approach, but it seems to be, at least gives you something for small dimension searches. So, and what we did was really just push it a little bit further. So we looked for extra information. So one thing you can do is you can look at your character table and of the algebra that you're expecting and rationalize it. If you know the Galois orbits, you can rationalize. When you rationalize the character table, it becomes an integer matrix, which would be just it wouldn't be R by R, it would be something less than R by R, but an integer matrix. And then you can use that integer matrix to add more identities, linear trace identities, to the generators of the variety. Every time you add a linear trace identity, which is independent, it reduces the number of variables in the search by 1. So that we took advantage of this. Okay. And then in step 4, you just have to find the non-negative integer solutions to this variety. Okay. These will give you all the CCVQs of a given rank and involution type. Involution type says is the action of the transpose on the basis. So it may move some elements, switch some pairs, but not others. And then you just have to try to solve this variety. The standard trick to solve this variety is to use the Grosvenor basis calculation in your computer algebra system. And that up to this point, I've been told many times that this hasn't worked very effectively. But again, I'm saying we're just being more persistent, and we're adding more things to our information. This approach does give you some things that are non-solutions. So because you can find solutions to the rational character table that aren't solutions to the character table, you can get yourself into some false solutions. So we have to eliminate those at the end, which I didn't say. But, okay, and then we have to check for non-cyclotomic eigenvalues, which we do with GAPS Galois type. Okay, so just to illustrate how this works, here's the rank 4 where you have one asymmetric pair of elements. So your basis is B1, B2, and B2 star. Okay, and so you create the regular representation, you put zeros where there should be zeros, ones where there should be ones, treat all of the other entries as variables, These regular matrices have to have the fact that the row sum is the valency, so that's why you see some of these are reduced, and the rest are completely variables. Now, when I apply all of the structure constant identities to these matrices, so I multiply the matrices and express them using the regular representation identities, it ends up giving me 16 different polynomials in this case. In our larger examples, we get lots and lots of polynomials, but in this case, it's not so bad. And then if I assume that the eigenvalues are non-cyclotomic, my Galois group of the splitting field over the rationals has to be transitive on the last three characters. And so they have to have the same multiplicities. So once I know that, then I know that the trace identities that I can add are quite simple. The trace of these matrices is given here. So I have two extra trace identities that I add to my variety. And then I reduce by taking out all possible linear substitutions. You can also use the fact that the multiplicity has to be positive to reduce some of these non-linear polynomials identities to linear ones and then use that. So anyway, you have lots of reductions that you do. And so the 16 polynomials just come down to 1. And so I can say that all of my rank 4 CETA-WIMs with one asymmetric pair are determined by just these constraints. Okay, and so now you can do a quick search of x5 greater than or equal to 0, k1 greater than 0, and positive integers, and find, try to find the very first non-cyclotomic example that you come up with. So that's the approach that we were doing. Okay. Now for, excuse me, I should go back. I skipped one. So we did this in rank 4 and rank 5. So it goes back to, I was asked in, I think it was 2011 at the BLED meeting by Noncyclotomic if I can do rank 5. He had already knew, I think, the rank 4 thing. So that'd be class 3, which I think Edwin Van Dam has a paper on. And we can, and this is what we found. So using this approach, your rank 4 with one asymmetric type, has to have cyclotomic eigenvalues simply because there's no central element of order 2 in a transitive, in a 3-transitive finite group, which is not abelian. This is S3 is centerless, so that basically eliminates that right away. When we solve the variety, we don't have to use the computer to solve the variety in the rank 4 symmetric case, but the BJs that we end up with, the matrices, are permutation equivalent. And so by Unamasa's theorem, we can say that those will be always cyclotomic. For rank 5 with 2 asymmetric pairs, so that's where the basis is B0, B1, B1 star, B2, B2 star. We solve the variety with the computer. There's something like 170 polynomials. We reduce to something like 8 polynomials in about 6 variables, and then show that those have to be permutation equivalent. Okay? And so those are also going to be cyclotomic. So basically, what I'm saying is if you assume you have an algebra, a CETA-WIM, that is non-cyclotomic, and you solve this variety, then you end up with this implication that the BJs are permutation equivalent. And in the rank 5 with one asymmetric type, so there you have 3 symmetric elements. When you assume that you have non-cyclotomic eigenvalues to solve the variety, you end up with a restriction on the Grobner basis with one ordering of your basis elements, or excuse me, one ordering of your variables, where the solutions have to be non-integral. And so you don't actually have CETA-WIMs that could be non-cyclotomic. And so you'd be done. But for rank 5S, we do find non-cyclotomic CETA-WIMs. So this is just a review of what the computer part is like. So the first case is where you'd have a 4-transitive Galois group. There things are a lot easier because your multiplicities have to be all equal. You have to act on the last 4 characters transitively. And when the multiplicities are equal, it means that the degrees also have to be equal. This is the pseudo-cyclic implies homogeneous theorem for table algebras. And so you can use that to search, to narrow down the search quite a bit. So your variety in this case is generated by 124 polynomials and 25 variables. One of the tricks that I like is to reduce to a rational basis of the polynomial space. So you get a different set of generating polynomials, and so it will have, well, it just has fewer polynomials involved. Same variables, but fewer polynomials. And that can cut down the computation cost quite a lot. And yet you still generate the same variety, or excuse me, the same ideal corresponding for your variety. So it's worthwhile to try that sometimes. When you do linear substitutions to that, so it's 48, you end up with 6 polynomials and 8 variables. And one of the restrictions forces the multiplicity to be even. And so now you only have to search for non-negative even numbers. And 3 other of your free variables need to be specified before your Grosvenor basis calculations can resolve the variety efficiently. And by efficiently, I mean absolutely instantly. You only have 6 polynomials, so there's not a lot of room, and your computer can do this pretty well. So we were able to search where the order, which is 1 plus 4 times m1, is all the way up to 1,000. And we found 6 solutions, which were non-cyclotomic. The one of order 249 is guaranteed to be the smallest, but the others were found using, a narrow search where there's about 10% discrepancy from, what we thought would be the average based on our first example. So we were able to find 4 more. Examples like this were known before. Hanaki has a paper, unpublished paper, where he has examples which have prime order that have 4 transitive Galois groups, and even rank 6 and 5 transitive Galois groups, where the smallest rank 5 example he has in that list is order 2713. The smallest rank 6 example has order 1973. But I think 473 is prime, so I don't know why Hanaki didn't find that one. So we may overlap the prime order results with that example. Okay, and we have a paper on our paper is posted on the archive. It's not published yet, but you can find these examples if you want to know more about them specifically. Here's the information for the order 249 example. So the multiplicity there is 62. The interesting thing that you need is these polynomials, these degree 4 polynomials that have Galois group isomorphic to S4. So what has to happen to have the algebra is you have to have 4 different polynomials with the same splitting field, and that means that there's if I adjoin one root of the one for B1, then I get a field which is not a normal extension, and all of the others have exactly one of their roots in that same field. So that's how this has to be. And the other being that you have a symmetric Galois group, S4 Galois group, the other roots can't be in that field. So if you would look at this character table, the one I've got down here, the first column is the roots of the first polynomial there. And in the first in the second row, you get a root which is in the same field as the first root of the first polynomial, but the others are in different fields. And so your Galois group permutes these fields the way it would permute the different fields that you get when you join one root. Anyway, that's how it has to be always with these algebras. You have to have certain kinds of, it has to be a polynomial configuration, which is quite subtle. Okay, and all of these 4 transitive examples are like that. In the 3 transitive case, the search is quite a bit worse. because there you don't have that the multiplicities have to be the same. Only the last three multiplicities have to be the same, but your first multiplicity, M1, could be completely different. And so now you have to use all the rational character tables. You have to search for every possible choice of M1 and M2. Anyway, you have to go, it's a lot more intense. So after about 2 months, we were able to finish a search of orders up to 100 and find 6 examples of non-cyclotomic CCVQs of order less than 100. And again, using a narrow search of orders up to 250, because we're trying to find the smallest ones, and we already had one of order 249. We found, I think, what was it, 10 or 8 more? Yeah, 8 more up to order 250. But this is a narrow search that is using things that are close to our first examples. Now, these small examples are interesting. So the ones I have in red or blue or gray are eliminated by some feasibility criteria that I'll talk about at the very end. But they're all a little bit interesting, and I'm sort of running out of time. So I'll just say that here's the example of order 35, which doesn't exist because it's not in Hanaki and Miyamoto's classification of order 35 schemes of rank 4. But it has an interesting feature, is that when you do a fusion of this character table, you get the character table of the complete bipartite graph. So if this existed, it would be a 3 fission of the complete bipartite graph, K7 times 5. Anyway, these slides I'm sure will be posted somewhere, so you can look at it later if you want to. When you calculate the dual parameters, of course, your Krein parameters have to be all non-negative, as you can see here they are, and they also have to lie in a non, they actually have to lie in the same field as K. So these minimal field of definition for the dual has to be non-cyclotomic in this case. Okay. Now, as I said, we've checked these with feasibility criteria, everything that we know of. So there's quite a few feasibility criteria for general symmetric association schemes that we try. So there's non-negative Krein parameters, handshaking lemma, triangle counts, absolute bound condition. I'm speaking in an algebraic graph theory seminar, so I'm sure everybody's heard of those. People who do table algebras know that you can make closed subsets, fusions, and quotients. And if you have an association scheme, all of those have to be also realizable. So closed subsets, fusions, and quotients have to be realizable. Recently, William Martin's student, Brian Kotelin, came up with a Gegenbauer polynomial criteria that applies to symmetric association schemes. You can find in his thesis on the archive. So this is a family of orthogonal polynomials that depends on the multiplicity mi that you can apply to 1 over mi times the dual intersection matrix, and that has to be a non-negative matrix. And just this year, there was a paper by Gavrila, Vidali, and Williford talking about forbidden quadruples, which we also can check, at least on our 4 transitive examples. So we've checked all of those, except for forbidden quadruple on the 3 transitive examples. We tried this, but the implementation it wasn't our implementation, it was Vidali's, and it never completed even 1 check. So we haven't been able to confirm that one. The order 35 example passes all the feasibility criteria that we have for symmetric association schemes, but it's not realizable because it's not in the classification. And so we don't have, feasibility criteria aren't good enough. Perhaps people have more now. Certainly that's an area of development these days. And let me just conclude with the last remark about realizability. We have tried to push the envelope on realizability. I've created a program that that at least gives us candidates to check for realizability. So if I have a CETA that satisfies the handshaking lemma, you can create a candidate. The handshaking lemma is the only barrier to creating a candidate for your n by n realized association scheme. And you can apply various metrics and moves to try to bring this to be closer to the association scheme. And so what you end up with creating is a permutation puzzle problem on the computer. And we have this implemented, but we just don't have a good way to come up with the ways to shuffle our candidate, our n by n matrix around so that it realizes the association scheme well enough. So we've been successful up to order about 70 in some cases for asymmetric association schemes. We haven't been very successful at all. Even order 31, it's a big fail. But for symmetric association schemes, we're getting reasonable performance from this up to about order 70. And so I'm just going to leave you with the thought that perhaps many of the questions about realizability that come up in this area are really questions where we should be interacting with people in artificial intelligence, because it seems to me that they would have the best techniques for covering that. Okay, and I'll stop there. I left a blank slide in case people have questions.
Thank you very much. Are there any questions for Alan?
So I have a question for the audience. I should have been asking more, I suppose. I'm sure other people have programs where they've tried to, attack the realizability issues. And I mean, I think it's something that would help a lot in this area. I think it has potential, but it's not easy. It's easy to get started, but not easy to get good performance from the programs. I mean, things like Conway's 99 problem, a lot of really important questions are really come down to existence of association schemes of that satisfy certain parameters, and compared to the finite group theory world, they look small. I mean, we should be doing a lot better at this realizability problem.
But if we were good at realizability, then that would mean, in principle, you ought to be able to easily determine the asymmetric schemes of valency K. And that's a major problem. Yeah, for a long, long time.
But I'm not talking about general K. I mean, if you fix one K, that's a different problem than
that's true. But if we were good at it, the situation would be quite different than it is.
That's right.
Yeah.
My point is, I think we're not good enough.
Well, yeah, that's for sure.